You can talk a little bit about networking. So what is a computer network? Anybody guess? What do you think? What do you think, Bernard? What is a computer network? Jose, what do you think a computer network is? Well, the internet is a computer network, but that's not what a computer network is. Understand? That's like saying, what's a car? And you say a Ford. Car, what's a computer network? Computer network is when we connect computers together to share information and resources. That makes sense? Pretty simple, right? And we got to connect them together through some type of media. What's a media? A media is what information flows through. So right now, what media am I using? What media? I'm giving you information. What is the information flowing through? No, my mouth's over here. You're over there. So what's getting from me to you? Air. So air is the media, right? You understand? So media is what information flows through, right? You understand? So we got Wi-Fi. What's the media for Wi-Fi? Air, right? Understand that? So media is what information flows through. So in networking of PLCs, we use primarily, we don't use very much Wi-Fi because it's open up, right? So just about all the type media that we use conductors. Are we okay so far? So there's been several ones that came out and used. One of the first ones was something called RS-232, which was basically it was a serial communication. And serial means what? So we got two ways we can send information. We can send information through what we call serial, or we can send information through parallel. Okay. Well, serial means we send one right after the other, right? So right now I'm using serial communication, right? Because all my words are just one right after the other. Okay. Parallel means we send it on through multiple medias. That makes sense. So your cable TV, is it serial or parallel? How many cables do you have plugging into your cable box? One. So it's got to be serial communication, right? So that means if I'm using 1024 by 768 pixels, then I would have that many wires coming into the back of my TV just to display one image. So images going up to this projector are serial, right? You understand that? Now, what advantage does parallel have over serial? Well, the analogy I use, it's just like a highway. You can have a single lane road going to Birmingham, or you can have a multi-lane road going to Birmingham. What advantage does a single lane, that's serial, what advantage does a single lane have? Well, it's a heck of a lot cheaper for them to build a single lane road from here to Birmingham, right? Understand? But what's the problem? All the cars are one after the other. I could still get 1 million cars to Birmingham, but it would take a while, a lot longer. So we take them interstates and we spread them out parallel. Now cars can go side to side, right? So it's basically parallel serial, but you can understand, right, the advantage of parallel. So parallel will always be faster than serial, and serial will always be cheaper using the same technology. That makes sense. So primarily, we use conductors. So our primary method is to electrically send information. And there's two things that I can send, two quantities. Now we know we got three quantities. We got voltage, right? We got current, and we have resistance. Now, which one of those do you think is most widely used? Voltage. Good guess. Voltage. So we just send voltage levels, right? You understand, to indicate information. Current is probably the second most, and we'll talk about the advantage of two. You're going to run into both of these in industry. The problem is when I mix voltage and current, of course, we can't have voltage without current, right? You understand? I'm sorry. If we send it between a source and a load, we cannot have voltage without current because everything's got some type of resistance. But we're looking at this thing right here where power is equal to I squared R. So power is what I pay for. I don't pay for voltage. I don't pay for current. So just about all systems that use voltages are what we call high impedance or high resistance circuits. So we can send a voltage level using very low current. Does that make sense? Now the problem we have with voltage is that we have something called electromagnetic interference. Which most people call EMI. And RFI is the same thing, but that would be radio frequency interference, right? You understand? And what happens is somewhere down the line, you have learned if I have a conductor and then I come over here and then I put a magnetic wave through that conductor, it's going to induce a voltage into that through what we call induction. So right now, I don't have my scope over here. I'm getting a voltage induced into me. I'm not a conductor, but I'm basically a semiconductor, right? Carbon-based line. So thank goodness they've made use of that voltage being induced into my body. And where do y'all run into that every day? So you have a touch screen, right? You understand? So I've got a voltage potential on my body. And if somehow I can couple it into this, into what we call a matrix. So if we was to split this screen up, it's thousands of these. It's got vertical lines and horizontal lines, and thousands of them. So when I come over and put my finger right there, I've induced a voltage into a column and a row, right? You understand that? And then the electronics that runs my phone is able to know exactly where I'm at on the screen, right? Of course, we have a lot of time problems with our fingers, so you can buy these little stylus pens that works a lot like a finger. And that's why if you wear just regular gloves, you can't do what? You can't work your phone. Now you can buy special gloves, guys. It's got little black little caps on the end, and what it does, it basically allows that electrical signal to come through. So we're constantly, when I deal with high resistance circuits, I'm constantly dealing with what we refer to EMI, where we induce information into the conductor that's not supposed to be there. And this is really critical in industry because there's a lot of EMI. So every motor generates EMI. Every conductor generates EMI, right? You understand that? So we're constantly fighting that. And we're trying to send digital information, which means digital information. If I change a 1 to a 0, then that can be telling your processor to wipe stuff out. So it's very critical that we try to do something about the electromagnetic interference. Now, one of the first things they did was, of course, when we send current, we've got to always have a return, right? So we have a source conductor, and of course in AC, the source and return are always doing what? Swapping. And then we've got to have a what? We've got to have a return conductor. Now normally what we do is we'll come up here and we'll make this one of these common. And common is nothing, just what everything in the whole system will connect to a common, right? You understand? So I might have series parallels and all that kind of stuff where the loads go through all different types of things. But eventually we're going to establish one of these conductors as a common. In house wiring, they call it neutral. That's the common in a house. And it's the white wire, right? You understand? So if I was to measure between the ground and the neutral, it would measure 0 volts. And then what electricians call the hot wire, that's the one that is not the common, right? Considered to be. So what was happening when we came up and do this was to help with safety. Normally what we would use is the common would actually be connected to earth ground. So it's, in these two terms are used, these guys are messed up all the time. Just about all the time we call the return a ground. And that's not true. And it's okay as long as you understand the difference, you as a technician understand the difference between a ground and a common. A ground means somewhere I've got a copper rod driven into earth ground and I've got a wire connected to that. That establishes earth ground. A common is just a return. So your car does not run a ground. Your car has a common. If it had a ground, then you would have a 1,000,000-foot long wire connected to a ground, right? Y'all understand that? So we don't run, we do a commons a lot. So what happens if we run a ground, 0 volts, ground is 0 volt reference, right? Even for Alabama Power and everything. So what was happening is we would come over here and we're trying to send voltage instead of power. We're not trying to send power. So we use high impedance circuits or high resistance circuits. So it requires very little current, which means I'm not paying $1 million just to run my sensors, right? You understand that? So what would happen is an EMI would come flying through this thing, and what it would do is it would generate a pulse in this conductor, and it wouldn't generate a pulse in that one because that's ground. Your power can't generate an EMF into ground, right? You understand that? Now this made things safe, especially for house wiring and stuff like that, because we use a lot of metal in house wiring, or in houses, right? You understand that? Because it's just a lot more sturdier. So your refrigerator is made out of metal, your washing machine is made out of metal, your air conditioners are made out of metal, right? You understand? Well, the problem is if we didn't connect those to ground, then they would build a charge because you're running them off AC. AC generates a change in. So what's required to induce an EMF? First, we know we got to have a what? We got to have a magnetic field. What else do we need? Hard to put this on every test and every class I take. What's the second thing we need to induce a voltage? Need a conductor. Just a conductor. A loop determines the amount, right? You understand? And then what's the third thing you need? Oops. We need motion. So the magnetic field has to cut the conductor. And what determines the amount? The amount of EMF or induced voltage. And the strength of the field. The number of conductor loops is what the card says like that. And the speed of the motion. So DC, unless the DC changes, if it's a constant state DC, it won't induce a voltage in it. And that's why DC is not passed through a transformer. Because that's what we're trying to do. We're dealing with this depending on how much current we get through a transformer. We're dealing with the strength of the field and the number of loops. That's why we can have more loops in the primary and less loops in the secondary, and a transformer will step the voltage down. If we have more loops in the secondary and less loops in the primary, it'll step the voltage up. So a transformer works with AC. A transformer don't work with DC because DC doesn't have what? DC doesn't have motion. So when we're dealing with these high resistance circuits, and we have both of them, we have one reference to ground and one not reference to ground, it's very easy to get a lot of EMI or electromagnetic interference into that conductor. Are we okay? So some of the things they did to try to correct this is we came up with what we call shielded cable. Which means we would take our two conductors and then around our two conductors we would wrap this inside metal. Because metals are good conductors, right? I would wrap this inside metal. Now shield is only supposed to be connected to, and then we would connect the shield to ground on one side only. Because if you connect it on both sides, you got a conductor. If you connect it on one side, you got an antenna. So what would happen if you connect it to both sides, it's almost impossible to keep the ground potential exactly the same on all sides. So I mean, if you got in your house and you got your meter, and your ground is usually over by your meter, your power meter. If you look, there's a metal wire running down from that, and it goes down, and there's a rod, and it's clamped onto that. Well, if you was to go on your other side of your house, and you had a big long lead on your voltmeter, and you was to hook it up on your ground, you would find you would have a difference in potential. Because it's impossible to keep ground over distance, right? You understand? So this is why big houses and big industries have grounds all over the place. Even if they're in a metal building, the metal buildings are grounded too, because if they didn't ground the metal buildings, they would build up a charge, right? You understand? So if you don't have a ground going to your washing machine, then, and you run it for a long time, you go up there and touch it and touch somebody that is grounded, you're going to get a little shock. Because why? Because there's nothing to get rid of that charge. So grounded on one side, and then we run a metal shield. This is shielded cable that's pretty expensive. And we did this for years. So if you ever take your TV cable off your back and you cut it open, you'll see it's got a metal wrap around it. What is that? That's the shield. That's coaxial cable. And what it does, it helps prevent EMI from getting into your cable. Works pretty good, doesn't it? Sometimes you can get lightning that gets through because that's millions of volts of energy. So what this then they figured out, and then when electronics came in, then they got operational amplifiers, and they came up and they created what they call differential amplifiers. This has changed the way that we send information. So a differential amplifier, and this became running a wire with a common. This became known as single-ended. This is what we refer to it. Some people call it unbalanced. I think it's unbalanced. So if you ever hear that term, it means it's a conductor running, two conductors running with a common. Well, when they came up with what we call differential, what they did is they came up with differential amplifiers, and differential signals do not use a common. Well, how can they send information if we don't have a common? Well, to send information, all you need to have is a difference in potential, right? You understand? Everybody okay so far? So the two interfaces that we use differential or balanced signaling. So we have two conductors. They're in close proximity to each other. And what we mean by differential is that whatever, and digital is easier to see. So let's say I'm sending digital information. And then what we have on the other conductor is it's a mirror image of what's on the first conductor. If I can do this. So all the signals are 180 degrees out of phase. Whether it's AC or DC or analog signals or digital signals. Now you can tell a differential signal by the way the symbols they use when you start looking at them. And this is not power, and this is what gets people confused, is we have these symbols right here. And what do we use those symbols for? We have these two symbols right here. And what do we use those symbols for? Well, you should know two things right off the bat. We use them for math, right? Tell us to do what? And subtract. We use them on DC power supplies, right? To tell what? We have the negative signal, the negative and the positive signal, right? We call them positive. On differential signal, the uninverted signal uses the plus, and the inverted signal uses the minus. So that's a symbol. A symbol, we use symbols to represent things, right? So it don't mean they're added together. It just means one of them's inverted and one of them's uninverted. And then on this side, what we'd use a differential amplifier. And notice here, we always have the ability to have a current flow because we always have a what? We always have the opposite polarity. So we're not using ground, we're not using a common. Neither one of these lines are considered to be a common. And what the differential amplifier does, it only passes symbols, or it passes symbols that are at signals that are moving in the same direction. Now inside your PLC, inside computers, it's all single-ended. So one thing the differential amplifier does for us is it takes a differential signal and converts it into single-ended signals. And then also it only passes differential. So what we'd get on this side is we'd get we'd combine them and we'd get that symbol like that. Now what happens if we got an EMI that flies through this thing, it's going to be a pulse there, it's going to put a pulse right there. And these are no longer what we call single-ended signals. These are what we call common mode signals. So common mode signals are signals moving in the same direction. And differential signals are signals moving in opposite direction. Does that make sense? So what a differential amplifier does is it passes differential signals but blocks common mode signals. If you ever look at one of the ratings on it is this CMRR. This is the common mode rejection ratio, and this is on the line of like 200 dB, which would be 2,000. They would divide the common mode signals by 2. I've seen them with 1,000 dB, which means it would attenuate it by 10,000. 1/10,000th of the common mode signal might get through the thing. Now to do this, these conductors have to be coupled precisely together. I mean, really close together. So guys, so what we do is we use what we call twisted pair cables. Now what's a cable? What's the difference between a conductor and a cable? Well, all conductors have some type of protection. The insulator would be some type of protection. Sometimes we have, so we have two things in conductors that we use. Of course, we have an insulator. What's an insulator used for? Yeah, it's to keep that push in, right? It's to keep the push in, right? You understand? So it's trying to push these electrons through, and there's no such thing as a perfect insulator, right? You understand that? So it's in there to keep, it allows us to put wires together, right? You understand, without, and it allows us to handle conductors without getting electrocuted. Then we have what's referred to as a jacket. So the jacket, it protects the conductor against the environment. Now, a lot of times these are one unit. You can't tell them. They're in there together, right? Understand? A lot of times it's not. So this white stuff you see around this is a jacket. This is a cable. This is the jacket. What's the function of the jacket? It's to protect it against the environment, right? You understand that? Where does this cable run through? What's it shaped against? How does it tear? That's the purpose of the jacket. If you got any Romax that we wire houses for you, if you ever strip it, you'll see that the conductors have a real thin, clear layer on the insulator. That's the jacket, right? You understand that? So some cables have multiple jackets. So basically, technically, a jacket, a cable is multiple conductors that share the same jacket. So this is a cable. Now, over time, it's became known as, we do have conductors that have multiple layers of protection, and those are often called cables too. So this is a cable. There's 8 conductors inside this, right? And they're all inside the wire, a common jacket. So what we use, and the telephone company was the first to use differential, is we use what we call twisted pair cable. And when we go on break, I'll come up and show y'all some of this. I'm going to use a different color, but normally in twisted pair cable, and we'll look at this, they'll have variations of the other color. And these are twisted together. Now what that means is that they're so closely coupled that when EMI, it generates a pulse in one, it will generate the same pulse in the other. And that's the advantage of twisted pair cable. So originally single-ended normally was good for about 50 feet. Ethernet, which is twisted pair, we can run this cable right here for 330 feet before we repeat it. And it's not because of the insulation, it's because of the drop in the cable. So unfortunately, we've always got to have current, right? Understand, anytime I have current, I send it to a conductor. A conductor has resistance, it will drop above. That means 330 feet on this cable right here. Originally, when we came out with all our instruments, all the instruments that we're using are the peripherals that we're using inside a computer. They use parallel, and they use single-ended. And we didn't call it parallel at the time. Pause this. I think I got it. So Ethernet uses this type of cable right here. It's a 4-pair cable, 8 conductor. I'll pass this around. You can see what we mean by a twisted pair. So they run in pairs. So one of them is going to be plus, one of them is going to be minus, right? You understand? For the same pair. And we have orange, white. We have orange, white. So it's orange striped with a white, orange. So what they do is they take the same color and put a white stripe on it. And we have a solid wire. So if I break this apart, it shows up, I'm going to pass it around. So this is white with an orange stripe, and this is solid orange. So that's one pair. We have green, white, we have blue, white, blue, brown, white, brown, and green, white, green. Those are the 4 pairs that we use in hardwired Ethernet. You see why it's called twisted pair, right? They're rated at a category. They use CAT for short. Currently, this is Cat 5e cable. So if you look at the jacket, you'll see I'm marking on there, and you'll see a Cat 5e. Basically, that defines the number of turns you have per inch. So the bigger the category, the more turns you have, right? You understand? So anything that connects to a network, we refer to as a node. And we have 2 types of nodes that I didn't see in this lecture. This is in the book, by the way. And the book's got some things that are wrong. We have what we call data terminal equipment. Data terminal equipment, these are DTEs. These originate the communication and they receive the communication. And then we have what we call data communication equipment. DTE, data terminal. That's an R, not an N, guys. These are the devices on the network that establish or communicate with each other. So this PLC is a DTE. This computer is a DTE. So a printer would be connected to a network would be a DTE. So these are the guys that establish and receive the communication on the network. These are DCEs. This is what the information flows through, not the media. These are the devices that the information flows through to get from between DTEs. So these are going to be your routers. These are going to be your switches. These are going to be your gateways. These are going to be your hubs, right? Does that make sense? But each one of them would be considered a node. And a lot of nodes have their own IP address. So a router has its own IP address. A switch has its own IP address. The hub don't. We'll talk about that. We don't use hubs that much anymore. Now what we do, of course, we've already talked about this. When we send data, we send it in what we call packets. We start off with something called a header. Then we have the data. And we have something they call a trailer. So the data has all your address and information. It has TCP, it has packet numbers. It's got a lot of neat stuff in there. It's got the link. It also maintains the length of the data. So that way we can send different data sizes on these things. And the trailer, this is where all your error detecting information is going to be. So you can look up on the internet what a TCP packet would look like, and it would explain everything inside there, tell you exactly how many bits and what all they do. So when we transfer information on the network, one device is not getting access to the network all the time, right? It's multiplex. Multiplex means we let multiple devices share the media. Thank goodness. So we're not going to talk a lot about DH45 and DH+. This is what some of y'all that use the RS-232 connector on your intro to PLCs. So the MicroLogic 1000. So if you have on one of the little suitcase PLCs, when you put intro to PLCs, those use the DH485 or the DH+. DH485 If you was on the 1100s, these guys use either DH485, which is this connector right here, which is something that IBM originally came up with. A DIN connector, a DB9 connector is a pretty good size connector. But IBM realized that they didn't need that, so they went to these DIN connectors. Let's switch back over. So this right here is the 485. This right here is Ethernet. And by the way, guys, even though if you buy your PLC and it doesn't support one of these, you can always buy a module that supports all the regular communication standards that are out there available to PLCs. If I couldn't do that, then I couldn't hook an older Allen Bradley PLC up to a Siemens PLC, right? Or share information between the two. So I don't have one, but the 1000s that's in the suitcase, this is the only guy they have available. And then the big 504s, they used a DB9 connector, which is what we use for serial. Originally RS-232, RS-10 is a bidirectional. It's in request send. Then it was the 232. That was the number that they were on when they standardized it. And then the one that we'll run into is RS-232C, which is the third revision of the RS-232 standard. It was originally standardized by the Electrical Industries Association, but they debanded back in like 1994. And all their standards turned over to the telecommunication industry standard, which is TIA. So when you look up RS-232, you'll find it either under TIA RS-232 or EIA RS-232. And it'll give you the pinout. It'll tell you what transmit data, receive data, and then the handshake lines. So we'll just look it up under RS-232. And see. So this is a DB9 connector. This is the way the cables look like. These are DB9 connectors. Now, notice they're up on a plateau. Let's see if it'll roll up like this. So these are female connectors, and connectors have gender. So female connectors are the one that has the holes, and then the male connectors are the ones that have pins. And on the male connector, it'll have a metal sleeve around that's in the shape of a D, and so you can't plug these things in backwards, right? Make sense? Okay. And each one of these pins, and it's called a DB9 because it's got 9 pins, right? Originally, RS-232 was a 25-pin standard. It was a dual channel standard. And they realized right off the bat that they didn't need dual channels to communicate with mice. So IBM dropped it down to a 9-pin connector. And this became the standard. And then they went over to this DIN connector over here. So most of your old computers, you won't see a big connector, 9-pin connector. You'll see a little round connector, which was a... So if you worked on one of the on the 504s, you see it would have a DB9 connector on there. If you worked on one of the 1100s, I mean on the 1000s, it had this little DIN connector on there. You can see this is keyed also. So you see it's got a flat side on it. And then it's got a ring on the outside. So the male connector would have a metal ring around the outside, and it would be flat on one side, so you can only plug this in one way. And of course, this one, this has a tab on the side that snaps in there that breaks off all the time, right? And so these you can only plug in one way too. This is called an RJ45 connector. I can't tell you what the RJ stands for, but this is the connector that we use for Ethernet, hardwired Ethernet. It's called the RJ45, and it's kind of like the one that we used on old telephones. It was called an RJ11. It snapped, and what happens all the time, you break off the little plastic tab. So most of the time on these cables, especially industrial cables, is they'll put something on here that protects that little snap right there. So you can see this cable, because most of the time what happens is people are pulling cable and they'll pull it, and then the little tab gets caught on something, they pull and it breaks it right off. A lot of times we protect that, and that's what the function of this guy is. So it's in there to protect that tab. So these are the cables that we'll make. So these guys get broke off all the time, and when they're broke off, what happens? Yeah, they slip out real easy. So these are the cards that we'll be putting in. So these are the cables that we're going to be making. These are provided by Siemens. We'll talk a little bit about these. So okay, so far. Questions? These have different names. In PLCs, we don't call it Ethernet. We either call it Siemens spec. They refer to this as Profinet. And then, of course, everybody else refers to it as Ethernet IP. Okay? Okay. Like I said, this is in the textbook. Of course, the conductors we use is coaxial cable or shielded cable. I think we use twisted pair cable. Everybody's okay on that now, right? Or fiber optics. You're not going to run. You might run into some fiber optics out there. I've never run into a PLC that has fiber optics capabilities, but I'm sure they're out there. What's nice about fiber, it uses light to send signals, and light is impervious to electromagnetic interference. So twisted pair almost eliminates, but there's still capabilities. If you get a lightning strike, even on twisted pair cables, it's going to get into it, right? You understand? But it's going to take a lot of energy to get into that. Fiber cables is impervious to electromagnetic interference. So, yeah, one of the, I think I might have told y'all the story, but when they originally was wiring up the network, using Ethernet or using what we call the star topology, and we'll look at that, is they had firewalls up in building A, and they didn't want to drill through the firewall, so they went up through one of the air vents at the top of building A, and they run this cable across the roof down through into a computer room. And we had a thunderstorm come through, and it blew out the network card in every computer in that lab. If that would have been fiber, it wouldn't have been care. So when we run up between building and building, inside the building, we predominantly use twisted pair cable. But running from building to building, they run fiber here on this campus right here. And it's usually buried underground, and so they don't have to worry about lightning out there. So I'll bring some fiber over here and show y'all that too. So coaxial cable, we already talked about that a little bit. It's got an insulated, it's got a jacket. It's got a what? Impedance, this is something we're not going to get into a lot. So this is called 100 ohm cable. It's got an impedance of 100 ohms, but that's not a DC resistance. It's not a resistance. It's something we call impedance. So when we get into AC, we run into these little things we call capacitors, and we run into these little things we call inductors. And these guys are what we call reactive devices. So what that means is they change their opposition with frequency. We talked a little about frequency in PLC, right? So on a capacitor, as frequency goes up, opposition goes down. And on inductors, as frequency goes up, opposition goes up. And they don't produce power. Current doesn't flow into them, current flows in and out of them, which is pretty neat. But they have opposition, and the opposition is ohms. Now, we could do that in this class, and I might do that. To get maximum power transfer between two devices, so technically impedance is opposition, that has both resistive and resistive and reactive devices. Opposition in a circuit. Should have put that. To get maximum power transfer through a system, all the impedances in the circuit must match. This is called impedance matching. So coax cable, we can get what they call RG58. I have to go back and look this up. I get them confused. One of them's got 75 ohm impedance. One of them's got 50 ohm impedance. I left out the C. Impedance is opposition in a circuit that contains both reactive and resistive devices. So I love my father-in-law to death, but he would do things. So that's back when we had these rabbit ear 300 ohm antennas. They were 300 ohm antennas. And so what you had to do is you had 300 ohm antennas, and then you'd run these, what they call a duplex wire down from the antenna, was 300 ohm, rated at 300 ohms of impedance. And we hooked it up to the back of your TV. It came into, it was, the TV was matched to what, 300 ohms. He took it off and hooked it up to his screen of his house. He thought if he made the antenna bigger, he would get a better picture. But the picture was actually worse because he screwed up the impedance matching, right? Does that make sense? And this is an AC resistance. It's not a DC resistance. So if you measure between this orange and this wire, if you measure between this orange and orange-white wire, it would measure infinity. If you put 100 kilohertz on that thing, it would oppose it by exactly 100 ohms. So you have to have special equipment to measure the impedance of the cable. So that's why it's important. If I'm running networking, I've seen people hook up these things and they'll stretch them out so they can crimp them into the connectors, and they'll leave about 6 or 7 inches, and they don't understand why their network don't run at 100 megabits. It only runs at 10 because it can't do what? So the first thing when these networks establish communication, they see how fast they can move. And just about all these things, these network cards are downwardly compatible. So if they can't run at 100 megabits, they'll automatically do what? They'll shift down to 10. If they can't run at 10, they'll shift down to what? To 5. And that's the worst they can do. He was pulling a truck through a big truck. He was moving something through his house, and he broke his coax cable running in his cable TV, and he just twisted the wires back together, and he couldn't understand why his picture on his TV was so bad, because he screwed up the wire. He screwed up what we call the impedance matching. And we can show y'all that, guys. It's really, really interesting. I'll try to bring that slide up and let y'all see, figure it out. So in your book, it says overall resistance. It's not resistance. Resistance does not vary with frequency. That's the definition. Resistance. By the way, all of these are in the glossary. There's a glossary up on the blackboard inside the handout. And this would be under the electrical section, right? So overall opposition of wire, it exhibits to varying opposition, right? You understand that? This is called impedance. And just about everybody, even though if there's no resistance in the circuit or no reactance in the circuit, you're going to deal with people when they talk about AC, they're going to use the term impedance instead of resistance. So basically, impedance sets up the impedance matching in the communication system. And then, of course, then the length would be the resistance, how far you can send it before you have to go through a repeater. Repeaters, these are devices that restore a signal to its original strength or amplify communication levels. So we run into repeaters all the time. So even a router, if you got a router, it's going to have two functions. Not only is it going to pick a subnet, it's also acting like a repeater, right? Understand? Also a switch acts. Are we okay? Lost anybody? So this is some of the cables. Notice these are shielded. This is the cable they use for DH plus. Like I said, these are not the ones we're going to spend a lot of time on. Twisted pair. Each conductor is covered with a coating of plastic and it's color coded. And we showed y'all what we're going to be using. It's got a standard color code. So even on this cable right here. So we have two types of twisted pair cable. We have UTP and STP. So TP, y'all probably know what that stands for, right? Twisted pair. This is unshielded. So what would this be? STP. So you're going to run into, so this is STP cable. You'll run into a lot of STP cable in the industry. Why? Because it's so dang noisy, right? Electrically noisy. All your motors, all the AC, all the three-phase, all the power that's moving through those cables that are unshielded, right? You understand? It's all over the place. So this is STP cable. So this is used in something called Profinet, and this is basically used by Siemens. And it's going to be green. If you're not using Siemens, it could be just about any color, but this is green. Arranged in pairs and twisted together to help eliminate crosstalk, but it's not only that's eliminating crosstalk, it's also uses that differential signaling, right? So you'll see most PLCs call this balance. So if they say this interface is balanced, it means it's a differential. Two major shielded, there it is right there. So we have shielded twisted pair, has a foil shield between the outer jacket and the bundle of conductors. Some have a shield around each individual pairs. I don't know what this is. I think this is single. When we was in Germany, we got the ability to make these things. It's pretty neat what they do. But you'll see we're gonna make these. We're running ours over a really short length, right? You understand? And it's not very electrically noisy in here, so we'll give y'all an opportunity of making a unshielded twisted pair. And this thing right here is cumbersome because your PLC is going to be right beside you while you're programming it, right? You got to deal with this. So we'll make ours probably about 36 inches long, and there'd be a lot like this. So DH45 uses shielded twisted pair, but it only uses two of the cables. 485. And I'll give y'all some more information on this as far as the lengths go and what type of signaling they use. So this is, we have two methods, and this is it. Let me get this out, that we can connect these. So we have what we call a straight through cable. These are the cables we use to connect the DTE to a DCE, or we use these to connect the DCE to another DCE. These are going to be the straight through cables. We have two methods of wiring them. We have what we call the TIA, which, as I told you, TIA is the Telecommunications Industry Association. Recently, this was established by EIA. But like I said, EIA was disbanded. We have the A connection. You got to do this right, guys, because you need these pairs to run together. And you just can't make up your color code. You just can't make up your color code, so we have an industry standard. So we have the A standard. Yeah, well, not match, because if you put brown and then you put orange side by side, and you hooked up your grounds, technically it would still, if you made them the same way on both sides, but then your twisted pairs would not be together. And if your twisted pairs are not together, so technically you could use brown, white, brown, and brown, white, brown on the other one just like that. But what you've done is you're not doing by the industry standard. And you get a networking guy out there, he'll look at these cables, and the connector broke off. He'll come up here and he'll wire it according to the standard, and nothing works anymore because everything is what? Twisted around. So these are the two standards. This is the standard that we use right here to make straight through cables. We use the TIA or the EIA 568B. But we don't make straight through cables. You won't buy a straight through cable, and you'll find this. And what's the color code? It goes orange, white, orange, right? Orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. So they actually deliberately switch two in the center, I guess, to make you. And we run them exactly the same way on both sides. To fool people, right? to put a Murphy in there. Are we okay? Now the problem is these are the two main pairs. So orange, this is the receive data, and the green pair, this is transmit data. And the other two are used for other things. So sending power. So we're using what we call voice over IP for our network. Well, the phones have to be powered up. But what they do is they use some of these other pairs to do what? To power up the phone. So if you was to plug our phone into a regular switch, it wouldn't work, because when they wired the college, they used two pairs for what? For power. Which ones they use, I don't know. So those are up to you what you can use those other pairs for. Now the problem is my PLC, my computer thinks it's a DTE, and my PLC thinks it's a DTE. So it's looking for information to come in on the what? The green-blue wire. Well, the problem is if I use the green-blue, I'm going to hook it into the transmit, right? You understand? So anytime I hook a DTE to a DTE, we have to use what we call a crossover cable. Crossover cable means we hook up one of the conductor, one of our connectors is hooked up using A, the other one's hooked up B. So y'all can go in here inside under the TV stand. It's got all the PLCs on it. There's a bunch of these green guys. Y'all can go over there and get these, and we can look at the pin. Let's see if we can. This thing's a yellow. No, let me take this. These are two crossover cables. This is what y'all gonna make. And when you look at one connector, you'll see it's orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. And then when you look at the other one, it's going to start off with green, white, green. We got two of them up here. So one of them is wired A, the other one is wired B. And we call that a what type of cable? Crossover. And both of those should have C's on the protector, so we know not to hook it up on a regular network. That makes sense? So of course, when we looked at these are crossover cables. But this has got a yellow connector on it. Are we okay? We're okay. So we'll start off. We're going to play around with the PLC today. We're going to try to hook it up and see if we can communicate with it. We'll let y'all start off using these, and then around next class, we'll let y'all make our own cables. So this is a crossover cable, but we've already showed y'all that, right? In your handout there. Fiber optics, we're not going to look at that. So a topology, this is the way we physically connect nodes to the network. And what's a network? It's a group of devices that want to share information and resources, right? The topology is the way devices or the way the nodes are connected on the network. Now, the first topology that they came up with, which is what we call it a bus topology. So this is a bus topology. So what we have is that we have one common conductor that runs the entire length of the network. And then the nodes tap onto that. Now, the problem is that this is just a piece of wire, and it's expecting to be we need impedance matching, right? You understand? So a bus topology is going to have a terminating resistor on each side. And it's just a resistor, guys. So if it's a 100 ohm cable, we use a 100 ohm resistor out there. It's got an impedance 100 ohm, and it's got to be on both sides. Now we have two ways. We have what we call a down drop, and I'll see if I can find the stuff that do here. So we tap into the cable. So we'd have one cable, which is our bus, and then we'd tap into the cable with a T, and then the device, then we have what we call a down drop. So this would be called a down drop bus. Another thing that we have is we have what we call a daisy chain bus, which means the devices just do like this. A chassis, I think in PLC of 1, I showed y'all the 504s, the 5/04s, the slick, what people call slick 500s. And it uses a rack. And then what it did is it ran a backplane down the back. And then you would buy a rack for a certain number of sizes. And then you could buy a communication module that you hook on the end that you could hook other racks together. And those other racks wouldn't have a PLC. They would be controlled by the original PLC. Now, what was nice about what would be the advantage of a rack-mounted PLC? What would be the major advantage of a rack-mounted PLC? We're not talking about PLCs over relays. That was one of the big advantages of PLCs. Not only was it programmable, but we didn't have all those relays doing the logic, which means it occupied a lot less space. One advantage, it's like my computer at home. My main computer at home is a desktop computer. It's got all the expansion buses. I get to choose what graphic card I get. I get to choose what I do this. I get to choose how many USB slots I've got. I get to choose because it's expandable, right? You understand? So the biggest advantages of a rack-mounted PLC is you buy what you want. You buy the CPU that you want to put in the thing. You buy the number of output modules you buy. You buy the analog modules. You decide what you need to run your company. So that is the major advantage of a rack-mounted PLC, is you get to do what? You get to buy exactly what you want. You don't buy more and you don't buy less, right? You understand? Well, what's the advantage of a fixed PLC? It's so much cheaper. But who decides how many ports you get? The company decides, right? So what you're trying to do is you're trying to find a fixed PLC because it's cheaper to match what you need. Either you don't match what you need and you still use some relay logic in a PLC, or you go out and get a frame out. Well, what they've done is what? They've combined the two. So what they've done is they've combined fixed PLCs with rack-mounted PLCs. So instead of having what we call a backplane where all these modules plug into, then what we have is we have a little cover that we can snap off the side. I might have to get the screwdriver. And then we can do what? Then we can add what we want. If I'm trying to do this right. This is for a SIM card. Oh, this might be it right here. So a lot of them are going to what I refer to as a hybrid PLC. So what you do is you snap off this, and the backplane actually comes through the modules, right? You understand? So what's nice about those is you got a certain number of fixed ports, and then you can do what? You can add what you want, and now you can more than tailor it. So more and more PLCs are using that feature right there, and I'll figure that out. So on the Siemens PLCs, the way this guy is set up is they have two sides. So the CPU is built in, right? You understand. And then we have a slot over here. So on Siemens PLCs, communication modules go into the left. So by default, this guy supports Ethernet IP. But what if I wanted to use DH45? Then we could buy a communication module. What if I wanted to use current loop? I could buy a current loop module, right? You understand? So the way these PLCs are set up, I/O ports go on the right, and then communication ports go on the left. We knock off this little thing right here, and you can actually see the backplane. And they're different, by the way. So some of the PLCs might already have the little thing off there. So there's the backplane. Definitely not parallel, because if it was parallel, it would have a ton of pins, right? So it's got to be serial, right? Differential serial, I don't know. We could probably look that up. So in this connector here, and hopefully this connector over here, hopefully it's different. Yeah, it is. So this one is shielded, right? So that way you couldn't put a communication module on the same side or vice versa. You could attempt it. Are we okay? Now this is where we can buy signal modules. We could probably look that up and see how many signal modules are available for the 1200. So technically still an S7 and 1200, and then we'll put signal board. Oops. So we have digital modules, we have analog modules, So what we do for the signal module, so we're going to use so this guy here's got 2 analog inputs built into it. And somebody lost the door off of this one. Here's analog right here. It's 0 and 1. Oops, let me get it up here so y'all can see it. And it's got 0 through 7. Remember, module numbers on the Siemens runs in groups of 8, right? And then the outputs. So we don't have enough outputs, I think. I think we got plenty of inputs, but we don't have any outputs. So we're going to put an I/O module onto the side. Okay. The signal module we have is we have a analog. Let's take this off. We have an analog module, an analog output module that we'll plug in here. Even though we don't use it, we'll let y'all play around. We'll figure out how to use it. So this is a DC, DC, DC. What does that mean? DC powered, DC inputs, DC outputs. Here, you got to be careful. They call their positive, they call it plus, they call it L, and they call their minus E. All we're doing is looking for the one that's got the arrow pointing in. Right? This is L1, L2. So mine is green for L1 and blue for L2. So down here on the trainer, the red is plus 24, the blue is minus. That means on this guy, we'll power this thing up down here. So what we'll have is we'll have our wires running from here down to this, right, to power up the PLC. Make sense? And when we turn the PLC on, it goes through a little self-test. Most computers do that. You see that? So we should expect this, right? So it's running this little self-test, right? Everybody okay? Oops. Now what we're going to do is, what's the 2 ways we can hook up DC inputs? Two methods. Yeah, but you got the right idea. But a PNP is a certain method, and an ETN is a certain syncing source. So first of all, before we hook up inputs, we got to understand which ones we're using, right? Understand? Now we're going to use the main power supply. We're going to be powering up a bunch of sensors. This has a power supply output down here. It has one on both the inputs and the outputs. So this is the power supply inputs for the outputs. This is the power supply inputs. This is the power supply output for the inputs. These guys are not designed to handle a bunch of stuff like sensors and everything. It would handle switches just fine. So if all I was going to use on the outside of my PLC was push buttons and stuff like that, then this guy right here would handle it just fine. If I was going to handle a bunch of solid state sensors, then this little power supply could not handle that, right? You understand? So we'd have to have an external power supply. So both the both the Festo line and the Amatro line uses external power supply. So what we'll do is we're going to use the power supplies that's available on out of the box. Okay. So when we power up our output. So we won't be using this right here. Now to play around with it first, we're going to use switches. And so what we're going to do is figure out what do we need to do. We need either sync or source, right? You understand that? Because if our inputs, if our input devices are sourcing, then my input to my PLC has to be syncing, right? You understand that? So this this guy here uses syncing input, so we're going to hook up our input devices to these sources. So what we're going to do, guys, is we're going to use these little signal switches that they provide. These are little signal switches. And by the way, these are not free. I don't give these away. I told the students last class that we had them in there, and they thought I was giving it to them. So we tried to carry them home. Did carry them home, but they had to come back. These are perfect switches to come in and loosen up these terminal boards right here. But what you're going to have to do to insert these things is you have to come all the way over to the power. Now, if you look, the only one that they have hooked up is this outside right here. This guy right here needs to go to plus. This is not hooked to anything. It's just going to screw into the minus. But understand that. And then each switch is come down here and it's going to connect to a certain output. So what we need to do, we got 8 switches. So we need to loosen up both our plus and minus. And we got to go down through at least 8 of them, right? And what we're trying to do is make room for the switches to fit in here. So it means I need to go all the way out to put 7. Oops. If I've got them loose enough, this guy should slide right in. Oops. I was trying to put it in the bin. It should slide right in, and what do we need to do now? Just go back and tighten them all down, right? We're okay? And then we should be able to power it up. Let it go through the theft test. You can see this guy uses LED outputs. Pretty easy, right? Any questions so far? Now, if you get we want to make sure we at least get 1 or 2 computers that don't have the TIA portal installed on them. So some of them's got these installed. I think last time we worked in groups of 3. I'm sorry, we worked in a pretty good sized class last time. The outputs we don't need to see. We'll just use the LEDs. We're not going to hook anything to the outputs. We're just going to kind of play around with it. I've got my programming languages up here in a folder instead of on the desktop. So we have two views. We have what we call the portal view, and then we have what we call the project view. By default, it's going to come up into what we call the project view. So what's the first thing I need to do? These are all the projects that's already out there. And I told y'all, by default, it's going to put it on our hard drive. So if we got any programs out there, we need to delete them, guys. So we're going to create a new project, right? And then what's the first thing we need to do? Give it a name. What's the next thing we need to do? Well, if we don't want to put it on this hard drive, we need to do what? Put it on your destination. Like if you got a thumb drive, that'd be fine, but you're going to be working with a group. Probably better just do it. Oops. The next thing I need to do. Configure device, right? Good. Okay, what's the next thing I need to do? Add a new device. This shows you what the TIL portal supports. So right now the TIL portal we have supports both the controller and the HMI panels. We're going to add a what? Controller. What's the next thing I need to do? Huh? Pick a control. Click a CPU, right? Where do I find this information at? The PLC on the side, right? Ours is DC 1214. Here's DC 1214 right here. And this shows the ones they're going to support. Where do we find this information? The actual true model number is going to be on the side of the PLC. Then we'll add it. Now what we'll do next when we start hooking this thing up is next we're going to add the I/O modules that we're going to add on the side. And I'm going to show you something they've done with Siemens that's really cool. We'll show you all that later. What's the next thing I need to do with the PLC? We need to configure the communication, right? I'm going to come over and click on this little green thing right here. And this shows us it's using the Class C IP right off the bat, 192.168. This is where we're going to make sure we don't all use the same one. So we'll have to figure out what the HMI panel is already using because it's already set up. And then we'll choose it. We'll still use Class Cs, but you don't have to use Class C. If you got a bunch of PLCs, on your subnet, then you might want to go up to a Class B, right? You understand? And of course, when you change it, you have to know that the subnet has changed. But since this is a Class C, 255.255.255, and the 0 gives us 256, and we're not using a router. Are we okay? That's why they get there, it popped up automatically, right? Okay. So what we can do now is we can so they call theirs OB1. So this is the same as ladder 2 on the Allen-Bradley PLCs. Ladder 2 and OB1 is the same thing. They call them organizational blocks. We're still not quite yet in this, and they don't call them rungs, they call them networks. So that's the big difference. And then over here, these are all your instructions. If it takes up a lot of room, you can slide it out of the way. It gives you more room to see if you need it back. So these are all the instructions, your timer instructions. We're going to be using those. Compare instructions, we're going to be using some of those. We're not going to be using math, we're going to be using move. Conversion would be like conversion from binary to ASCII or BCD and stuff like that. These are your most often used, and I'll show y'all later on how you can actually add instructions as you're going to use all the time. So we can come over here and we can start off with a push button. And what's it waiting on? It's waiting on a logical address, or address that we assign, right? So on this one, it's a little different. We start off with I for N, right? Then we start off next with the byte number, so byte 0. Then we put a period, and then we put the bit number on that module that I want to. Then we hit enter. What Siemens does is it automatically. Oh, I put an O instead of a 0. You put 0.0. Now what it does when we enter it, it's going to automatically assign it a tag. And they'll go in sequential order, 1, 2, 3, 4, 5, 6. And this is what Allen-Bradley called symbols. And that's what I required y'all in that, because just about all your PLCs now, all Allen-Bradley and Siemens PLCs are tagged-based applications. 5000 will require you to assign a tag. Siemens, if you don't assign a tag, it'll just give it a name, which gets very confusing. So we'll call it, we can come up here, right click on it, and it says rename tag, and I'll show y'all later on how you can do your tag table first, which is the way we'll work on it. So we're doing on the fly tags, right? And I'm gonna we'll call this a stop. Okay. So now I don't have to use this address, I can use the tag instead of the address. And then we'll pull this down. And by the way, it's really neat. So if as soon as you start typing in the tag, there's going to be a little window, a little scroll window that pops down that shows you all the tags that start off with that name. So it's really, or start off with the first letter or the second letter. Keep reducing it the more letters you put in. And then you can just go down there and select it. You don't have to type it in. If you start off with a tag, let's see if this works. Then notice it gives us an underline, which means we have an error. And then we can go back and do what? We can define the tag. I'll have to go back and figure that. Some way we can enter the address right there. So let's go back and delete that. And I'll figure it out later. So we're going to call it input 0.1, right? So this is our down drop. So it's not going to Allen Bradley, when you pull your down drop in there, it puts the whole loop. This does one loop at a time. Then we can come up here and put our, right here. Oops, wrong thing, Rich. Okay, then we can come up and put it up. I like it. It draws it a lot like motor controls. Then we give this a name. Output, no, here we use Q, right, for outputs. Then it's asking for a tag. I'm right clicking on this, by the way, rename. And then over here now we can just call this what? Run. See what popped up and started showing you? Okay, so there's my program. By the way, it automatically sticks to networks. Are we okay? Any questions? All right, so what can we do now? We got two options. We can download it and we can't upload it yet because there's nothing in the PLC. Now what's going to happen is the PLC hasn't been configured yet. So the first time you're going to do this, it's going to pop up and it's going to tell you it needs to go out there and find this PLC that you said is out there. So this would be like, kind of like RS Links, where you can go up there and hit that and it tells you. So it's going to find the PLC. So what we're going to do is we're just going to go out there and start the search. You see it's searching. Oh, it says it didn't find anybody. Why didn't it find anybody? I didn't find anybody. We'll start, got a bunch of X's down here. We'll start the search again. By the way, Ethernet provides two lights. One light is referred to as link. This means you've got a connection. And then it's got a yellow light that flashes when it transmits data. So if you plug in your cable and that link light don't come on, it either means the cable's bad or you're using the wrong cable. You're using a crossover cable instead of, that makes sense? So this is the first light we're looking for right here. So there it is right there. It's got, this is the MAC address. We understand that now, right? You understand? Then what we can do just to make sure is we hit that flash LEDs and you can see what it's doing. So that means now we know we got what? Good connection. Are we okay? And then we'll put load. If it's got a PLC, it's got a program in there, it's probably going to come in and says it's out of sync, which means the program that's up there doesn't match the program you're trying to upload and all. Compiling, we know what that means now, so it's literally taking the program written in the high-level ladder language and it's converting it over to binary for the PLC. Says we have some download to device, download to device, download to device. Sometimes it wants you to do little things over here. It'll put a little scroll button over there. You go back and tell it to do it and sync it and stuff like that. It looks like everything's okay here. So we're going to load this in the PLC. And then we're going to start it. Right. Okay. Now, what we're going to do is up here you got these little glasses. See the glasses up there? This is what you turn on to monitor what's going on there. So I can come over here right now and I can flip these switches and nothing happens. And why is that? Because I'm not monitoring. So on this Allen Bradley, here you need to monitor. And what I like about this is it shows you the entire flow. So right now it's showing me my power is setting right there. Because my stop button is supposed to be normally closed, right? Okay, see that? And we can come over here and just flip the start switch, it seals in. Okay. And how do we stop it? I'll let her, or switch. So remember, we have to use an examine if. We have to use an examine if closed, right? You understand? For a normally stop push button because it's normally closed, right? And that people coming out of motor controls, that gives them a big problem because in motor controls we use a normally closed push button as our stop button. And it's drawn as a normally closed push button on your motor control screen. But here we draw it as we use a normally open because the normally open says it's true when it's closed. That's what examine closed. So guys, y'all want to try this? All right. You can connect multiple EC sources. Parallel and series. So why would we connect them in parallel and why would we connect them in series? Right. So the way the power supply is wired up, and we need to hook them up series 8ing, right? So this is the connector on here. This is on the right hand side. This is the red one. Then we come over here. We got another connection right here. This is what they call, hopefully they don't call it ground. They call it common, right? Because it is a common. And then over here, the other power supply is like this. And then this is yellow. So this is our minus power supply. This is our plus power supply. And it's common and they're both variable. So how am I going to get 24 volts? If this one only goes to 15 and this one only goes to 15, how am I going to get 24 volts? Well, I'm going to take the plus and put it over here. I'm going to take the minus and put it right there. I'm going to adjust this up to 15 volts and I'm going to set that to 9. They're hooked in series 80, but here's series 80 to increase voltage, right? You understand that? So there we go. We got 24 volts off our power supply. Are you okay? We're not going to use the common, right? That makes sense. Okay. Or you can set this to 15 and that 9. It don't make any difference. And it's close enough. You don't even need to get your meter out, but make sure you put it on the 15 mark. Don't go past the 15 mark. And make sure you put it on the 9 mark. And there's enough leeway in the PLC itself that will compensate it. We could look it up and see what maximum and minimum voltage it requires to operate. I think it'll operate all the way down to 20 volts. Are you okay? Any questions there? So we got two wires here. I got a A green one and a blue one. That's the colors we have. And they've got banana, they got the male banana connectors on the end. So this allows you just to plug them directly into the trainer and then hook it up to the plus L and the M, right? The one with the arrow pointing in, right? Not out, the one that's pointing in. So that'll be, don't lose the little doors. So that'll be the ones with the arrow pointing in at the top of the PLC, the first two on the left. Huh? You need to hook the minus to the yellow, right? And then whichever color you use. They use blue for common or minus. So if you go ahead and use that, like I said, these are the only wires I have. I think I gave y'all green and blue. So on mine, I'm using the green for the plus and the minus for the blue. So on Siemens PLCs, your plus is L, but the L will usually have a little plus sign behind it, and the M is the minus. Everybody understand that? And they won't put a minus sign beside the M in their PLCs. Must be some German word or something. I don't know. Hoyt. I spent a lot of time in Germany. He can speak a pretty good deal of German. Nancy learned how to cuss a little bit, which is funny. So one thing you're going to do, you're going to have to realize if you work with PLCs, you're either going to have to have an external. If you get one of these little old Surface Pros or something like that, you're going to have to get an external CD or DVD reader, right, player, or you're going to have to buy the PLCs with them, and that's usually what we do. Because just about all your applications for PLCs are going to come on the DVD now. We should have 2 DVDs in here. One of them has the Step 7 version 14, and then one of them's got one called PLC Sim, which allows you to run it through an interpreter and check your program out instead of actually going. Another thing that they do is inside this is going to be a USB drive that you cannot use. This is the license for this thing. You got 2 types of license you can get for PLCs. You can get a yearly license or a 365-day license. So if I was to bring out some of the other ones, it's got 365 days in it. And after 365 days, it does, after installation, it becomes invalid. So you have to redo that every year. Allen Bradley, what you do is you get a sheet of paper that's got a code. So Allen Bradley, you got to have internet connection on the computer because that's the way you download the license. So on Allen Bradley, you actually download that license. Siemens, you're going to come up and get these. And either they're going to have a permanent license. A permanent license you pay a ton of money for, right? You understand that? Then a yearly license you pay. So our Allen Bradley license is a yearly thing. And we pay like $250 per computer for 1 year. But if you got Factory Talk license, if you bought it outside, it's right around $18,000 that your company's paying for the Studio 5000. So that's the way our license is. The license we're going to be putting on here, these are permanent license. And so what's happened somewhere during the installation, it's going to tell you to do what? Stick that on there, right? And if you needed to, like if you was going to upgrade computers, you could take the license back off, put it on the USB stick, and move it around. So literally, you could have it on 15 computers, and all of you would do what? Share one stick. You'd have to come around and stick it in there all the time on the computer that's running it. Well, we're going to download them. So these are permanent license. We get these, we get this whole package for the 1200 plus the permanent license, plus the little simulator, plus the analog card. It's like $250. So, but that's education. Y'all can't get that. And that $275 for the Allen Bradley, that's education. If you're out there in industry, ain't no way in the world you're gonna license that software every year for that much money. They want to give education a really good deal, because usually the people that come in and learn PLCs, that's usually if they have the opportunity to buy the PLC, then they buy the one they already know how to use, right? So we should start off with this guy, right? If it's not on there, and it should auto load when you stick it into the DVD. And then next thing you need to do is use this one, and then these are your update connections. These are what we call service packs. When operating systems first came out, when you got your version of DOS, you got that, that's what you got. And when they came out with changes, they would come out with a different version. It would be like DOS 5.1, so that means that would be the second. And you would have to go out and buy 5.1 to get what was added. But now what do they do to support the operating systems? If you've got an internet connection, they keep your operating system updated for you, which is really neat. Costs on. So any questions? So anybody need to install it? Yes. And I want y'all all get involved with how to install this. So instead of us is everybody else has already got T on there? Yeah, that's not set. So y'all come up right here and let y'all all watch this install on one computer. See if y'all can figure it out before y'all start on it. Okay? So if you go in there and you're going to install it, if it's got that plastic cover off of it, it means it's already been installed. Just where y'all can get room. Where y'all have room. So this will be fine if you don't do it up here. Well, we've got some more power plugs right here if y'all want to go back to the back. You just had a chance to rewire them. Right here. That's fine as long as all y'all can get around.